Hi everybody, hope you're well. Thank you very much to those of you who submitted the work last week. It was good to see some of you got on okay with class notebook. I think that'll be useful in the weeks to come. If you didn't quite manage to do it in class notebook, don't worry, it's just important that we get the assignment in. So at 6 o'clock on Sunday just now, there's still a few that have not completed it, so I'm hoping that there'll be a few more done by the morning. But if you haven't completed it, it is very, very important that you have a goal. Obviously, the quizzes that we normally do are good sort of feedback and information for us, but they are all multiple choice, so not ideal for us checking your working and how you're getting on with setting out your equations and your explain questions and things, which you know is what most of the final exam would be set on. So it is really important that you have a goal at the assignment. If you do have any issues accessing it on class notebook, there is a digital copy in the file section, so it's better that you send it to us via email if you can't do it in class notebook than not at all. Okay, so for this week we're moving on. We're moving on to a sort of new topic completely, so not really anything to do with what we've been doing the last couple of weeks with our electric and magnetic fields. So we're moving on to a new sort of subtopic called irradiance. So this is, like I say, it'll be completely new to you. There's not a huge amount to it, which is why we've decided to pick it for this week. So just again a reminder of where to find the information. Go into Files, Particles and Waves Materials, and you'll see that we've set up a folder called Irradiance. So this is all your materials you're going to need for this week. If I have a look at the checklist just now, you will see that there is a wee bit less on it, and the reason for that is that this is a short week, that you're off on holiday Friday, Monday, Tuesday, so we wouldn't have had as much time in class, so slightly less tasks this week. We're also going to ask you to complete the tasks by Thursday the 11th of February. And the reason for that is because it's really, really important that you do take this weekend off, that you do enjoy the holiday and try to get away from your screen as much as possible. So we didn't want to set it for Sunday as usual because we don't want you to be working Friday and Saturday. Now what that means is when it comes to issuing the assignment, we're not going to wait till Wednesday. I'm just going to upload the assignment today. So you've got the 4 days to complete the tasks and complete the assignment. You're not waiting till Wednesday to get it. So the tasks for this week, watch this short video here. In a couple of minutes, I'm going to talk you through some information about this week's content on Irradiance, but there's also this video on YouTube, which is another physics teacher talking through it. I'm pretty sure it's the guy from Glasgow Physics. It sounds a bit like him, so if it's not him, he's definitely stealing the patter, but he talks you through Irradiance, and it's all at higher physics level, which is important because there's obviously a lot of information out there, but you might not necessarily have to know it for higher physics. So it's a Scottish teacher talking the higher content. So hopefully you won't say anything that I don't, but it's good to have the different resources to have a look at because it is, like I say, very new. BBC Bite Size, as always, is really good. Again, it's tailored for higher and it's got the key information. So have a look at that. You may have noticed that I've added BBC Bite Size as a tab on your Teams page as well. As usual, you have your notes booklet, so it's pages 39 to 42. It's got all the information about irradiance, so have a read through that. Make your own note on irradiance. So Bite Size will really help with this, but also your notes in your booklet. So remember, try and keep your notes really brief and clear in terms of what you need to know. So to help you out with that, I would be looking for a good note to include the definition and units of irradiance and both equations associated with it, which I'll talk about in a minute. You may also want to refer to an experiment because that tends to come up when we talk about irradiance, but again, hopefully that'll make sense shortly. And then as usual, you have some problems to do and the solutions are uploaded for you. So after you do that, it's going to be your assignment. The assignment is going to be like a quiz. So multiple choice questions, and like I say, that'll be loaded today. Okay, so learning intention success criteria. We are learning about irradiance. Success criteria for this week is that you can define what is meant by irradiance and state the units, and then solve problems involving irradiance power and area, and solve problems involving irradiance and distance using the inverse square law. So hopefully you can see from this quite short success criteria list that for irradiance we really just need to know what it is, and then there are 2 equations that relate to it. So like I say, a short topic. Theory can be a wee bit tricky at points, but hopefully if you just keep yourself right on knowing the definition and the 2 equations, then we'll be okay. So I'll talk you through fairly briefly about irradiance just now, just a sort of introduction. Again, I don't want to be here for an hour, but hopefully I'll set the scene and help you understand what it is we're talking about. So irradiance is probably a completely new word to most of you. If it helps you to understand what it is we're talking about, irradiance used to be called intensity of light or intensity of radiation. So what we're dealing with here, and nearly all the questions we'll talk about, we will be talking about light. But again, we disclaimer, whenever we talk about light in physics, we could be talking about infrared, ultraviolet, or whole EM spectrum. So it's all to do with the intensity of light. So that's what irradiance is. So what I want you to think about is if you've got a bulb, okay, and that's giving off light. Now it's important not to confuse it with brightness here. It's not the same thing as brightness. It's about the intensity of light. So if we think about a sort of bulb, and we said it's got like a 50 watt bulb, so that's its power rating. So it's telling us that 50 joules of energy are being transferred every second. So that gives off that energy. I want you to think if you were standing right here next to the bulb and your eye was there, you would be exposed to quite a big intensity of radiation. Don't do this, by the way. This is theoretical. So if you were right next to the bulb, you would experience quite a lot of radiation in your eye. If you were back here, you would experience less radiation. Now, the important thing here is that the power of the bulb hasn't changed. So the energy transferred per second hasn't changed. However, what you're experiencing in terms of the intensity of the radiation has changed. Now, what we mean by this, a better quantity then for us to measure, rather than just deal with the power, because the power doesn't tell us the full story, what we deal with is irradiance. And that takes into account, well, yes, there's energy there, but how is it being spread? How is that energy being spread? Now, annoyingly, the symbol for irradiance is capital I. You're maybe going, yeah, that is annoying, because we know that capital I already has a quantity, which is current. Sorry about that, but it's got the same one. We just hopefully keep them separate. So what we're dealing with here is what happens to this energy, this power, when it is being sort of dispersed over a larger area. So how we think about that is, well, first of all, when we're dealing with bulbs, we think about them as being like we call it a point source. Now, a point source means that it is radiating radiation in all directions. Okay, so that's important. For irradiance to work, we're dealing with point sources. So it means our radiation is going off, and that's where the word radiation comes from. It's like the radius of a wheel. So the radiation is being emitted in all directions, and that's what makes it a point source. Now, in reality, a bulb isn't a perfect point source because it's not floating, because there must be something at the bottom of it to keep it up. But we can think of a small bulb as being close to a point source. So it means the radiation is being sent off in all directions equally. Now, if I just take this little section here and say, right, I've got light coming off and it is covering a certain area here. Okay, so all of that radiation that's coming from here and here and all in here is going to cover this area, and that's what you would be exposed to if your eye was at that position. Now, if you were moving further away, we would see that for the same amount of radiation that's been emitted, it is now covering a larger area. And that's why, if you were at that position, you would experience a reduced intensity of radiation. It's not that the energy or the power of our bulb has changed, it's just been diluted almost. It's been spread over a greater area. So here, it would be much brighter than what you would experience here. Now, if we were in class, we would be demonstrating just now with a balloon. So if you took a pen and drew a little square on a balloon before you blow it up, so if you took a black pen and coloured in a little square on a balloon, you'd see that it would be quite dark with the pen. But if you blow up that balloon for the same amount of pen, it would spread out and the square would become fainter and fainter. So it's a good way to think about irradiance. So, well, what does that mean in terms of our definition then? Where does that come from? So rather than just deal with the power on its own, to get our definition for irradiance, we're talking about the power over a certain area. Now, we know in physics then, that just becomes our equation. So it's the power being, and fancy physics word here, dissipated over a particular area. But that is our equation, that's our defining equation. So when we've got an equation that actually tells us what the quantity is, it's our defining equation. So what we would say is the irradiance of our source. So normally, I think about 80% of the time and higher, we talk about it being visible light, but again, could be any of our EM spectrum, is equal to our power over area. Okay, so it would be whatever the power of this lamp is, divided by whatever the area is here, or whatever the area is here, and that would give us our irradiance. Now, if we were in class just now, I would be asking you, well, what are the units of irradiance then? So it doesn't have its own special units. It doesn't have like watts or joules or volts. Its units are derived from the equation. So hopefully you're doing this just now while you're listening, but I can't check. You would be thinking, well, power is measured in watts. Area, now we haven't really covered area much in physics, but hopefully you know from maths. Meters squared. Because our equation is divide, our unit for irradiance is watts over meters squared, or watts per meter squared. So that's where our -2 comes from. So that is our unit for irradiance, watts per meter squared. And again, you can always just work that out using the equation. So the first equation is pretty straightforward. You normally are just given the power of a source and area, so nothing too difficult about that equation. You'll have the opportunity to use it. But I did say that there were 2 equations that you'll need to use. And the second one is a little bit trickier, and it involves something called the inverse square law. So you have met the inverse square law before, and that was when we were doing gravitation. So it's similar to that. So we've got our light source here. And again, to help us understand the inverse square law, I'm going to talk about our little cross section here. So this is giving off our radiation, and it's covering this area here. Now, we should already sort of be aware that as the distance from the source gets bigger, then the area that it covers gets bigger. And because our radiance is divided by area, if you're dividing by a bigger number, then irradiance is going to go down. So it's looking at a relationship here that as Sorry, that should go up there. So as our area gets bigger, our irradiance is going to decrease, and our area is going to get bigger as we move further away from the source. So if we think about, say this is 1 metre here, what we're looking for here with this equation is what is the relationship then. So if we're 1 metre there and it covers a certain area, if we go another metre, what's going to happen is the area is going to increase along this way by 2, but also up the way by 2. So the area is going to have increased because we're dealing with a point source, remember, so our light is being emitted in all directions. So we need to think about our 3D shape. So it's covering a length times breadth here, but the length times breadth here is going to increase by 1 this way and increase by 1 up the way. So it's now covering 4 times the area. So if we see here, we've got double the distance, but 4 times the area. Now, if I increase this even more, I'm struggling to fit it in here, but hopefully you can see, and we made that 3 metres, then it's going to have increased along by an extra 1 and up by an extra 1. So we're now got 9 times the area for 3 metres. So hopefully you're starting to see a bit of a link here. So, sorry, that should be a 1 there. So an extra 1 metre. So hopefully you're starting to see a link here. So as we double the distance from the source, our area is covering 4 times the area. If we triple the distance, the area is now 9 times. So we've got 1, 1, 2, 4, 3, 9. So we're dealing with a square here. And this is what I mean by the inverse square law, because we're looking at the relationship between irradiance and distance from our source. So we can say that first of all, they are inversely proportional. So inversely proportional means as one gets bigger, the other one gets smaller. However, they're not. It's not just as straightforward as saying inversely proportional, that when we half one, we double the other, or when we triple one, we third the other. It's more complicated than that. It's an inverse square law. And what that means is that it's inversely proportional to the square of the distance. So the irradiance is inversely proportional to the square of the distance. So it means if we were to double the distance, the irradiance would drop by 4. If we tripled the distance, the irradiance would drop to 1/9 of its original value. Okay, now I might have lost you a little bit here, but again, bear with me. I'm trying to do this fairly quick so you're not all listening to this for too long. Where we have met this before, like I say, is in our gravitation equation. Okay, but what it means is whenever we have an equation with our proportional sign, how to get rid of that is to times it by a constant. So if we call our constant k, our equation becomes this. Now this equation on its own isn't particularly useful because, well, if we know the distance, then we can know what the irradiance is going to be. However, when we tend to use this more is similar to when we use our gas laws in National 5. So when we can use it is basically if we know what the irradiance is at a certain distance, using the inverse square law, we can work out what the irradiance would be at a new distance because we know that it equals a constant. Okay, so if we know that I1 equals k over d1 squared, then I2 also equals k over d2 squared. Now what this means though is if I were to bring this up here, or this up here, it means that I1 d1 squared is equal to a constant, but I2 d2 squared is equal to the same constant, which means our equation eventually becomes I1 d1 squared equals I2 d2 squared. And that is how we talk about our inverse square law for irradiance. So it's an equation like any other equation. So even if you haven't followed me with where it comes from, don't worry too much. You're just going to treat this like any other equation. Basically, if I know the irradiance at one point and the distance at one point, remembering to multiply it by the distance squared, and then I know the new distance, then I can work out the new irradiance. Or if I know the new irradiance, I can work out the new distance. Don't worry about the ones and twos. Doesn't matter which one comes first, the equation will still work because it's equals. They're the same on both sides. So hopefully you're going, oh yeah, that reminds me of pressure and volume in my gas laws at National 5. And it's the exact same idea. So it's really useful in terms of trying to work out. So I know that the irradiance of this object was 2 watts per metre squared at 2 metres. What's it going to be at 6 metres? And you can just plug in those numbers there and you can work out your new irradiance or work out your new distance. So this is called the inverse square law for irradiance. And it is really, really useful. But as usual, it's not always that straightforward. You need to be careful with a few things. The most important one is remembering the squared. Common mistakes from pupils when you're doing the questions is to forget about the squared in these equations, especially if you're rearranging for distance, because you're going to eventually have to square root when you're rearranging the equation. Okay, right guys, I'm well aware that I have fired a lot of information at you there, but hopefully that will make a little bit of sense. But as usual, you're not going to know totally how you understand it until you start doing some questions. So the problems you're going to do this week, you'll be happy to know that there is only 5 questions on irradiance and the inverse square law. So using both of those equations. And then there are 2 exam style questions that you can have a go at as well. But it is, like I say, it's quite a small subtopic. It kind of stands on its own a little bit. So not a huge amount of questions to do, but enough to get some practice with it. There are a few that talk about experiments and how you would go about this. And essentially, you know, it's basically what I've drawn there. You would take a bulb, you take a meter stick, you would measure the irradiance at different distances, and you would plot your table and your graph to get your information from it. Again, there's more information on that in the notes, so it might be worth having another read at that before you answer these questions. So just a couple of pages of questions that you can try in Irradiance, and then the solutions are uploaded as well. So remember just to check your work as you go. The solutions are here. Okay, so like I say, new content for you. So please make sure that you're asking for help. We didn't have many on the calls last week, which is fine because it was a consolidation week. But if you do need any help with any of it, then please make sure you're asking for it, that you're coming on to the calls. That's what we're there for. We don't expect you to completely understand everything just by watching, you know, a 15-minute video. If we were in class, we'd be spending a lot longer going over it. So please ask for help. Try not to, you know, become too overwhelmed and switch off. It's not going to be easy, but we can just try our best. Last thing I'll just say, it's just come into my head there just to clarify. I spoke at the start about it being a point source. So normally we think of little bulbs as being point sources. So that's fine. We can also think about stars as being point sources. In fact, they're quite often better point sources because they are technically not floating, but they don't have anything holding them up. What we can't think about as being a point source is a laser. Now, lasers emit light all in the same direction. So it's just worth pointing out that at this point you'd have an irradiance which would be the exact same as this point here. So the inverse square law does not work. Okay, it does not work for a laser because a laser is not a point source. The inverse square law only works for a point source. With a laser, the irradiance would be the same at all the distances. So just watch out for that when it comes to the questions. It will only work for a small bulb or a star or a planet that's reflecting light as well, but not for a laser. Okay folks, best of luck with this week's work, but again, please speak to us if you have any questions. And again, just a reminder that the assignment is due for Thursday this week.